Welcome to today's lecture. We will continue our discussion on application of fluid inclusion microthermometric data to understand ore forming environments, and here we are particularly be dealing with the hydrothermal environment, where the mineral deposits result from the activity of hydrothermal fluid, and that hydrothermal fluid could have diverse sources. Before we attempt to discuss, we have already seen some such examples. We should keep in mind that the literature on hydrothermal processes and the resulting mineralization, the wide spectrum of ore deposits of a number of important metals, is actually too vast to be summarized or to be reviewed or to be synthesized in this lecture series under the time constraint. And so, we will be just picking up some of the important examples just to demonstrate that how the fluid inclusion microthermometric data have been interpreted will all be based on the different workers, the way they have interpreted, and without actually going on to any kind of a critical evaluation of that. And the other thing to keep in mind, that the information that is coming from the fluid inclusion microthermometric data is definitely a vital piece of information on any deposit that is resulting from hydrothermal process, but then at the same time information generated from other sources such as mineral thermometry and ratios of stable isotopes like oxygen and carbon, they do also contribute towards understanding of the origin and evolution of the hydrothermal deposits, which we will not be discussing here now. And there are other things to keep in mind, is that we do categorize the hydrothermal deposits into different genetic types based on the origin of the hydrothermal fluid. But when we see the deposit wise, individual deposits in any particular terrain and also the across the geological time scale, then we do find that they do differ in sometimes in very significant ways from each other, and we, even though we always intend to put them under certain specific genetic categories, there are deviations from the common theme that generally we try to formulate. Nevertheless, it is of course one of the exercise in ore geology to categorize deposits into genetic types and then to explain observed deviations in different possible ways. And the other important aspect is that the hydrothermal ore forming environment is in operation in the earth's crust right from the very beginning of the evolution of the earth's crust. So, we get such deposits as old as the Archean times to even the present day situation that is happening in the ocean floor hydrothermal systems as well as land based geothermal systems. Now, let us have a brief look on this particular diagram, which is taken from the book of Lawrence Robb on Introduction to Ore Forming Process, where it is a kind of a synthesis or categorization of the different deposit types based on the source of the or the nature of the water or the hydrothermal fluid, which is arranged in a depth increasing depth condition. So, this meteoric water, shallow circulating water, meteoric water, and the deep circulating meteoric water, then water which is trapped in the pore spaces of sediments, the cornate water, metamorphic water, magmatic water, and the deposits that we get are listed here. And from the arrows marked here, we generally know that what kind of deposits play their role in formation of such kind of deposits. It is of course not possible to take each, and there could be some other deposits which may be missing here, for example, the uranium, the vein type uranium deposits and the unconformity associated uranium deposits like the rich ones occurring in the Athabasca basin in Canada or in the Alligator River basin in Australia and some other places, where we know that These are rich sources of uranium mineralization, uranium resources, and the pegmatites, of course, which sometimes are important from metals like tin, tungsten, niobium, tantalum, and also some gemstones. They are the fluid, they also need to be placed somewhere here. And then out of this, we will definitely be more interested to see which type of deposits we do get representative ones or the well studied one in the Indian context. Some of the deposits which you do not get well studied or well documented in the Indian context, still it would be worthwhile to look at their characteristics in terms of the fluid, nature of the fluid, the sources of the fluid, and the way the fluid has been interpreted to have been evolved during the entire spectrum of hydrothermal activity. So, for example, the orogenic gold deposits or the low type gold deposits, they are well documented in the Indian context in the Dharwar Craton. We do not have typically the Carlin type gold deposits which occur in the younger rocks in Mesozoic and later, like what happens in the Western American Cordillera, Western American, the Basin and Range province in the states of Nevada. The famous Carlin type gold deposits which contribute, which are rich sources of gold right now, we do not have such representative as of now known to be occurring in the Indian subcontinent. The porphyry copper deposits are also absent in the Indian shield, bearing the deposit Malanskhand deposit, which has been discussed in some amount of details about the fluid inclusion characteristics, which sometimes is debated to be having a affinity like porphyry copper ones. Then the tin tungsten Gryzen deposits, like already the one, the Gryzen or the Skarn, the one which we have already discussed about the Dachang deposit in China. We do not have also much of Indian occurrence, and the iron oxide copper gold deposit, the famous the Olympic Dam deposit, the epithermal deposits, the high sulfidation and the low sulfidation epithermal deposits, which generally we find in the Pacific ring and mostly in close spatial association with porphyry copper deposits, is the high sulfidation one and the low sulfidation one deposits like the one in Hishikari in Japan and some of the other deposits like the Lihir Island, the Ladolam deposit in Lihir Island in near Papua New Guinea. They are also not represented or not known to be documented in Indian context. The sandstone hosted, the tabular type Colorado Plateau uranium deposits, often of late there are some deposits in the northeastern part of India are coming to be known. As we know, the Indian shield as well as the extra peninsular India still need to be explored for the occurrence of many types of deposits, and this VMS, the volcanogenic massive sulphide deposits, the typically the one, the Kuroko type and the Cyprus type, they also are not very well known. Of late there are some deposits in some occurrences in the South Delhi fold belt and which are, and also in the central India, which are being described to have close similarities with volcanogenic massive sulphide deposits, but the only problem is that they are deformed and metamorphosed. So, their original characteristics are lost, but still they could be studied to understand the fluid characteristics. And the Mississippi Valley type deposit, they are also a very interesting class of deposits displaying very peculiar, very interesting fluid characteristics, and the copper in the red beds like the Kupferschiefer, the juncture of the red bed and the black shales, where the Jambian copper belt and the Kupferschiefer are not well represented in the Indian context as well. And now, if you look at many such deposits which are characterized with their fluid characteristics, it is always observed that they do have identifiably multiple sources of fluid. For example, in the orogenic gold deposit, which is very well known to have been resulted from metamorphogenic fluid in the greenstone terrains, they also do have fluid components which need to be ascribed to other sources, sometimes a magmatic source or a meteoric fluid. A meteoric fluid is a fluid which can percolate to greater depth and can interact with any other type of fluid to give rise to mineralization. sometimes the conditions, for example, in the iron oxide copper gold deposit as discovered in the famous Olympic Dam deposit in the Gawler Craton in South Australia, and there are many such deposits which are prescribed in the periphery of the close spatial association with the Olympic Dam deposit, occurring in the same kind of Brexia complex in granite in intracontinental granite, Proterozoic granite. So, there sometimes the fluid characteristics need to be to involve fluids of magmatic sources, or sometimes such kind of fluids also are ascribed to connate sources whenever we get a temperature a little higher, but the salinity to be representing something intermediate or little higher than the that observed in meteoric fluid. Sometimes the it remains conjectural as to what exact source we should ascribe. Similarly, in a volcanogenic Nassau sulphide deposit, we would expect that it would be the seawater to play a dominant role, but sometimes we do also get fluid inclusions and characteristics which indicate much higher salinity ranges to be, so that some magmatic sources or some kind of process have to be invoked in them. So, the gist is that sometimes the fluid sources remain conjectural, and the fluid inclusion data have to be supplemented with other information like stable isotopes and mineral thermometry. So, within that framework, still what we find that yes, the fluid inclusion characteristics in terms of salinity, temperature, and now with the availability of precision and sophisticated microanalytical techniques, it is becoming a little easier to actually characterize the fluid in terms of their ore bearing potential, or which actually carried the metals. For example, in case of the porphyry copper deposit or in case of the orogenic gold deposits, there are many instances in which the inclusions are analyzed with the topic which we will be discussing in the later part of this lecture series about the microanalytical techniques, in which various metals could be analyzed directly from the inclusions, either by destroying them or in non-destructive techniques. So, this is how the science is being forwarded, and we should always keep some of the limitations in mind while trying to apply the fluid inclusion data to understand different types of deposits. So, I would like to give a little bit of idea about the low type deposits in the greenstone granite terrain, and we know that in the Dharwar Craton we have occurrence of such deposits which have been producing gold for almost more than 1.5 centuries before, like the one which is Kolar, which is shown here. This is the Kolar schist belt. This deposit has been closed down because of the falling grade of gold with depth, and it is one of the deepest gold mine in India. And some of the presently working deposits in the Hattimaski schist belt here and in the Ramagiri Penakacharla, they are also not currently producing. Some deposits are in the Chitradurga schist belt, in the western Dharwar Craton, which are also being still some exploration and discovery are being done. So, if we examine typically, I will just go by the example of the Hattimaski schist belt and the inclusion. So, what exactly is done is the loads, the quartz and the quartz gold loads, or the quartz gold sulphide loads, which are present within the meta basics, which are essentially amphibolites or altered amphibolite, or to alter to a chlorite grade kind of rock, and they are present as loads in the schistose rock. These quartz is sampled from this kind of these loads, and so one thing was also we should keep in mind while interpreting or trying to use fluid inclusion data. It is always necessary to have a very good understanding about the general geological setup, the constitution of the ore in terms of the mineralogy of the ore and gangue minerals, and the overall and the deformational phases, the stages in which the ensemble has evolved, because finally that is what is going to be integrated to build up the story of origin and evolution of any particular hydrothermal deposit. So, taking the example of the Kolar gold mine, which was studied some time back. So, the inclusions that we see in the Kolar gold mine in the different reefs, which are the gold quartz reefs or the gold quartz sulphide reefs. So, they are aqueous biphase in this. So, the two different types of lodes, one is the gold quartz lode and the gold quartz sulphide lodes were studied from the Kolar region in two different mines, but they are the same lode which is exposed, and the aqueous biphase inclusions, aqueous polyphase inclusions which are restricted to the Champion lode, pure carbonic restricted to the again the Champion lode which is essentially gold quartz lode devoid of much sulphide, and the aqueous carbonic inclusions also restricted to the Champion lode. So, that means when we come to see the lodes, the pure gold quartz lodes seem to be the ones which contain the appreciable carbonic component in the fluid compared to the ones which are the gold quartz sulphide, where the carbonic phase seem to be lacking. And so, when we observe this data, so the fluid inclusion the microthermometric data are generated, and then we know that we could use them in constraining the pressure from intersection of isocores wherever we get coeval existence of pure carbonic and aqueous inclusion from their isocores. We do also can constrain the minimum pressure of entrapment from the aqueous carbonic inclusion from the total homogenization temperature, which the methodology which we discussed, and also the aqueous biphase inclusion by their freezing runs can see their salinity and temperature distribution. So, we get the ranges in which it definitely indicates that the fluid in ranges in the salinity and temperature from low temperature low salinity to high temperature, low salinity to high temperature moderate salinity kind of fluid, which may not be that very easy to explain by invoking only one source, but more or less a fluid which is a low saline carbon dioxide bearing fluid. Possible metamorphic derivation was ascribed as a ore fluid, and from the pressure temperature estimation that was made from the isocore intersection and from the aqueous carbonic inclusions, some kind of a path, this kind of evolutionary path was deduced, and it conforms or it agrees with the fact that the original fluid which is or the parent homogeneous fluid which is an aqueous carbonic fluid carried or transported the gold, and with the drop of pressure this particular fluid got separated, underwent unmixing, and that unmixing is witnessed by the coeval existence of pure carbonic and pure aqueous inclusions, from which from the intersecting isocore further evolution of the fluid to the lower pressure temperature conditions could be deduced, and a picture of evolution of the fluid with the change in the physicochemical parameter mostly pressure and temperature that could have given rise to the mineralization in the gold quartz lodes could be ascertained. At the same time, when we find that the lodes, the aqueous component fluid is also pretty high in its salinity, going to 40-50% weightage from the polyphase aqueous inclusions. So, here the it is from the gold quartz lodes, and this is from the gold quartz sulphide lode. There we see that even in case of the gold quartz lode, even we get cell fluids which have much higher salinity. So, that is why the situation led to proposition that the fluid definitely a high saline fluid definitely which should be in its identity to be close to a fluid could be of magmatic derivation must have been involved. Okay. So, look at similar such situation from the Hattie-Muskee schist belt. We know this is the map of the Hattie-Muskee schist belt, where this is the presently producing mine Hattie with multiple lodes shown here, and here there is one deposit which is very close to the granite, the younger granitic body Yellagatti granite which is exposed here. This is the Ooty deposit, and here there are Wandali and Hirabudini prospects which are also within the Hattie group of metaphasic rocks. And so, fluid inclusion studies were conducted in the Hattie and the Ooty deposits. I could give a comparison here. What we could see from the similarly, we see aqueous biphase inclusion, pure carbonic and aqueous carbonic inclusion. Similar thermobarometric exercise when combined with the metamorphic conditions of the host metabasic rocks as well as some mineral thermometry, combinedly give a picture of the evolution of the mineralization in the ore fluid, which is interpreted to have been initially been derived by devolatilization reactions in the prograde metamorphic path of the host metasediments, and then with the further drop in pressure and temperature condition, the fluid also underwent unmixing, phase separation to carbonic and the aqueous component, which resulted in drop in the solubility of the metal and deposition of the metals in different loads. As against that, so here in this situation of Hatti, we see that there are occurrence of carbonic, the fluid has an appreciable carbonic component. If the deposit which is within just about the northern part of the Hasti-Mesquite schist belt in close proximity with the younger granitic rock, there the fluid inclusions examined with, it was observed that this particular fluid inclusions were sampled from the quartz in this deposit. There was no carbon dioxide bearing inclusion which was observed. It was only the aqueous biphase and the aqueous polyphase inclusions, and there the temperature salinity plot also do give some idea about the changing nature of the pressure temperature conditions during mineralization, and these are the isocores of the extreme density aqueous inclusions which are observed, and this kind of box is coming from the alteration conditions in two different stages, and these are the much later situations where the low pressure temperature kind of alteration situations, which combined with all three give a picture of evolution of the ore fluid. So, here the point only to be noted is that if we ascribe the auriferous ore fluid to be derived only from a single source like a metamorphogenic source, and that fluid could be characterized by a low salinity carbon dioxide bearing and sometimes with appreciable amount of H2S or any other sulfurous species, then the scenarios in some situations seem to be different, and so where fluid of a possible magmatic derivation also could be speculated. Here some results which were obtained from the Ramagiri Pennakucherla schist belt also need to be worthy of discussion. These are some of the field photographs from the Ramagiri Pennakucherla schist belt, where we see the quartz veins within the metasediments, and that is what exactly the way the mineralization, even we sample the quartz from here, we also do get occurrences of gold grains along with sulfides, and these are the typical occurrence in the Pennakucherla and Ramagiri schist belt. And the fluid inclusions, when we examine, we also do get the aqueous biphase, and here if we look at this map, then this is the Ramagiri schist belt, this trident shaped here, and this is Anandpur, this is Pennakucherla. So, they are all surrounded by younger prolific younger granitic activity which are exposed in the as shown in this map here. To the left of this is the major granite body, which is a closed pit granite, which is a prominent granite body in the Dharwar Craton, roughly marking the boundary between the western and eastern Dharwar Craton here, but this belonging to this particular granite body belongs to the eastern Dharwar Craton. So, we have a scope of sampling the quartz and study inclusions in the veins within the metasedimentary rocks like here in the Ramagiri Pennakucherla schist belt, as well as the matrix quartz in the granite and the quartz veins and pegmatitic material in the granite, so that we could possibly establish a relationship if at all exists between them. So, these are some of the ways the fluid inclusion petrography has been done, taking the sample and then the magnified area is shown here. There are all the 4 types of inclusions: aqueous biphase, pure carbonic, aqueous carbonic and polyphase inclusions. They occur in almost all these host minerals in coming from the schistose rock as well as from the granite. There are subtle chemical differences, for example, the aqueous carbonic inclusions which occur in the veins and pegmatitic materials and the matrix quartz in granite. they are pure carbon dioxide without any methane being in them, whereas the quartz veins which are occurring, the auriferous quartz veins in the schistose rocks in Penachurla and Ramagiri, there the carbon dioxide carbon dioxide has appreciable methane in its in the fluid, which are detected by laser Raman microspectrometry as well as from the depression in the melting point of carbon dioxide. So, we see the assemblages is quite heterogeneous, like the one which has been shown here. You could see in the same samples aqueous biphase inclusions of low salinity carbonic aqueous carbonic inclusions, and sometimes very high saline inclusions exemplified by polyphase halide bearing daughter crystals here, and the coexistence of pure carbonic and pure aqueous inclusion, and also very interestingly some high saline aqueous carbonic fluid which are having some daughter crystals in them, which gives us an idea that there must have been some multiple source of the fluids in this particular area, and that is how it gives us a heterogeneous. These are some of the interpretations which could always be having there are some interpretations which would always have some different opinion, and you could see the aqueous fluid scenario here where the histograms are plotted. So, the salinity variation we could see going from almost near very low saline near 0 to salinity value as high as 50-60% with the inclusions which are represented as the polyphase inclusions here. So, they are the quartz veins in the schistose rocks, these are the quartz veins in granitoid and the matrix quartz in granitoid, and the temperature also what we observe here, the temperature of homogenization which are not pressure corrected go to values 300-400 degree or above, and we see that the distributions of the aqueous biphase or the aqueous polyphase and the situations where the dissolution of halite is more than that of temperature homogenization, or the reverse situation, they more or less have a good overlap in the temperature interval. And when the data are plotted on a fluid evolution diagram, we could see a complete continuum in the fluid, and sometimes we also do get high saline fluid without having any daughter crystal present in them, because of the many of the regions that we have discussed before. There could be saline highly saline fluid, but not of the dominantly chloride type, and so the different inclusion types are plotted here. As you could see the symbols, the squares plotted from the quartz vein in the schists, where we could see a continuum, and the solid circles the quartz vein in the granitoids, and the triangles representing the matrix quartz in the granitoids. So, here we see that they do have very interestingly overlapping characteristics. And then when we synthesize the information all together, we could rationalize, or we could develop, or we could formulate some kind of hypothesis as to what could have happened in this particular mineralizing system. So, when we see that the inclusion characteristics which are sampled from the granite, either the matrix quartz in them or the quartzofeldspathic veins within the granite, do have a very interesting overlap with the. So, this is constructed from the aqueous carbonic inclusions in the magmatic domain and also the aqueous carbonic inclusions in the ore domain, where they do represent situations which correspond to higher pressure temperature conditions, because they represent the situation in which the fluid was miscible in the miscible regime, higher temperature pressure conditions, and that there we find that there is a very high probability that this particular granite during the time of its crystallization evolution, during which a fluid phase generally exalts out of the granite in the process of second boiling, or even in cases where there has been no second boiling, but the fluid could have just evolved at a greater depth conditions, and there is a good overlap between the pressure temperature regime deduced from the granitic domain and from the ore domain, and so these intersection points are from the coexisting or the coeval aqueous carbonic, pure carbonic and the pure pure carbonic and the pure aqueous inclusions, which give us a good range in the evolution of the pressure temperature conditions of the fluid combinedly, and these are the situations in which the coexisting pure aqueous inclusion H2O NaCl and the pure carbonic inclusion is shown here, and a similar situation from the different ore resins. So, that leads us to building up or the formulation of kind of a hypothesis on the origin and evolution of mineralizing system in the Ramagiri Pennakarchirla auriferous schist belt, so that it gives us an idea that or the possibility that there is the fluid considering its temperature salinity ranges and the similarity in the fluid characteristics in the host granites and the ore domain to have such kind of a evolutionary picture. As I have said that these kind of interpretations could always be equivocal and need to be substantiated from data from other sources like isotopic data, or sometimes even by analysis of individual inclusions from by some destructive or non-destructive microanalytical technique, or sometimes even we can analyze by bulk kind of destructive analysis like the cross-Leach analysis, which also will be discussing later on. So, these are some of the examples of the mineralizing systems, hydrothermal mineralizing system, and in particular the cases that we discussed about the low type gold deposits, which are also known as the orogenic gold deposits in Archean granite greenstone terrain, and how the rationale here the idea is not to get into any kind of debate on the what has been proposed or what is right or wrong, but it is only the way the microthermometric data have been used and what kind of logic has been applied. So, we will continue our discussion on the application of microthermometric fluid inclusion microthermometric data to other type of hydrothermal deposits in the next class. Thank you.